Hello students, myself Dr. Shuhit Gupta. Today in this video we will study radioactive decay. In the previous video we have talked about some decays: alpha decay, beta decay, gamma decay, positron emission, electron capture. There we have studied in a very short manner. Now we will study it in a broad manner. First decay that comes in the picture is the alpha decay. In this alpha decay, as we have already studied that its daughter nuclei will have Z-2 protons and its total number of nucleons decreased by 4, and we will be getting a 1 helium nuclei in the form of alpha particle. Why this is happening? Because the size of nucleus is too large in the case of alpha decay. Now what about the decay constant? As we know in our lower classes that decay constant is denoted by lambda. But lambda depends upon two factors. First one is nu and second is t, where nu is the collision frequency, t is the transmission probability. Now what is collision frequency? We can define it as the ratio of velocity upon 2r, where v is the velocity of the alpha particle with which it is moving from the nucleus, and r is the radius of the nuclei. The one thing that we have to learn and memorize is the collision frequency is of the order of 10 raised to power 21, and the kinetic energy of the alpha particle is equals to half mv square. Now what is the collision? It is basically the collision that is occurring between alpha particle and the barrier, because alpha particle collide with the barrier to get out of this barrier. So nu is the collision frequency of the alpha particle with the potential barrier, and it is of the order of 10 raised to power 21. Now t is the transmission probability, and transmission probability is inversely proportional to the strength of the potential barrier. Higher the height of the potential barrier, let's suppose this is a potential barrier and this is the our alpha particle. If the strength of this potential barrier is much higher, then the transmission probability of the alpha particle will be very small. So transmission probability depends on two factors, that is the energy of the alpha particle, secondly, and strength of the potential barrier. So if the strength of the potential barrier increases, transmission probability starts decreasing. Now second decay, that is beta decay, that we have already studied. Its basic reason is nucleus has too many neutrons relative to the number of protons present in a nuclei. In this case, daughter nucleus having Z increased by 1, but the number of nucleons remains same, and in this case one electron is emitted from the nuclei with one antineutrino. We can also consider one example from here, like in the case of carbon, when one electron and one antineutrino is emitted, carbon turns into a nitrogen. We can also check the instability like by taking the ratio of number of neutrons and number of protons. The number of neutrons in the case of carbon is 8 and number of protons are 6. But in the case of nitrogen, the number of neutrons and protons are same, so their ratio is 1, and because C614 is unstable, so it tends to become stable by beta decay and it converts into nitrogen. Now let's move on to our third decay, or we can say positron emission. This is also a reason of instability of a nuclei. In this case, nucleus has too many protons relative to the number of neutrons. Like in this case, suppose this is our nucleus in which it contains a large number of protons than that of neutrons. Then what will happen, that one positron would emit from the nuclei with one neutrino, and it will result to a daughter nucleus with atomic number less than 1 and mass number remains the same. Now what is the reason of electron capture? The reason being is same like that of positron emission. In this case also, nucleus has too many protons relative to the number of neutrons, but what happens in this case, is electron gets captured by the nucleus and it becomes a daughter nuclei in which atomic number like number of protons decreased by 1. We can also consider the example of this copper. By taking one electron from the orbital motion, copper turns into nickel. Sometimes examiner may give you a question in which he will ask about the reason of instability of any decay. Another decay that we will study is the gamma decay. In the case of gamma decay, the nuclei which is already in the excited energy state, it turns into its ground state with the release of some energy. So the reason of its instability is the nucleus has excess amount of energy. We can consider the case of strontium 38 in which its mass number and its atomic number both remain same but with the release of some energy. Now let's turn on to our next topic, which is the radioactivity Soddy law. This law was given by Rutherford Soddy. In this law, it states that the disintegration process of nuclei in a sample is a matter of chance. Like it is not happening that first alpha decay will occur or then beta decay will occur. It is just a matter of chance. So it is a totally statistical process. Second, in this case, when the disintegration occurs, different isotopes would have different half-life. Third law, it states that half-life of isotopes depends upon the decay constant. The T half is directly proportional to the decay constant, which is denoted by lambda. Fourth, the speed of radioactivity does not depend upon temperature and pressure. Rather, it is independent of temperature and pressure. Fifth is a radioactivity. As we have already studied in our BSc and MSc classes, that radioactivity is directly proportional to the rate of disintegration, which is directly proportional to the disintegration constant and the number of nuclei present, and the negative sign here representing that the number of nuclei are decreasing with the time. So if we plot a curve between the number of nuclei and time, we will get that at the 0 time there will be n naught, means that is the total number of nuclei would be present, but with the increase in time the nuclei starts disintegrating and it decreases in this form. It decreases in the exponential form. Why it is decreasing in the exponential form? This is because number of nuclei is related to the disintegration constant in the exponential form. So n is equals to n naught e raised to power lambda into t, where t is the time in which the sample of the nuclei turns to its this amount and it decays exponentially as e raised to power minus of lambda into t. We can also write lambda into n as an activity of the sample. What we will do, we will just multiply this equation by lambda on both sides. We will get lambda n is equal to r and lambda n naught is equals to r naught e raised to power minus of lambda into t. Another expression that we must remember, that the half-life of any radioactivity, expression that we must remember is a half-life time of a nuclei. It is a time when the total number of nuclei becomes half. So it is inversely proportional to the decay constant. So it can be written as 0.693 upon lambda. And what is the average lifetime of a nuclei? It is the time when the life of nuclei becomes 1 by E times the number of nuclei present. So mean life of a nuclei is inversely proportional to 1 upon lambda. Sometimes examiner would ask about smallest unit of radioactivity. So it is a 1 becquerel and it is equal to 1 disintegration per second. Like in 1 second, if 1 nucleus get disintegrate, then this unit is known as a 1 becquerel. Second unit, that is 1 Rutherford, which is related to 10 raised to power 6 disintegration per second. Like in 1 second 10 raised to power 6 nuclei gets disintegrate and The largest unit of the radioactivity is the 1 curie, which is equals to 3.7 in 10 raised to power of 10 disintegration are occurring in 1 second. Like these number of nuclei gets disintegrate in 1 second. So all the 3 units that we must remember. Next is a Gamow theory. Next is the Gamow theory of alpha decay. Now, what does this theory says? Now let's move on to our next topic, which is the Gamow theory of alpha decay. What does this theory say? According to this theory, that there is a small probability of alpha particle to cross the barrier, although it is not possible classical mechanically. Now let's turn on to our next topic, which is the Gamow theory of alpha decay. Now what is actually happening inside a nucleus? Suppose we have a one nuclei, which is a large size nuclei having Z greater than 92. This factor you should also memorize that, but the value of the alpha decay would occur if the mass cut. Now let us study the Gamow theory of alpha decay. Now this theory of alpha decay is occurring for the case of large sized nuclei with Z greater than 92. Now if the size of the nuclei is very much large, then there will be a formation of alpha nuclei inside our present nuclei, but the kinetic energy of the alpha particle inside the nucleus is of the order of 4.9 mega electron volt. But suppose this, let's suppose this is the barrier potential that alpha particle has to cross, and the strength of this barrier potential is 25 mega electron volt. Is it possible for a particle with energy less than the strength of the potential barrier to cross it? No, right? But this is possible in case if we do not consider alpha particle as a particle, if we consider it as in the form of a wave. This is what the Gamow theory says. Like this is not possible classical mechanically, because when we consider alpha particle as in the form of a particle, but it is a possible in quantum mechanically, because in quantum mechanically we not consider the alpha particle as a particle, we consider it is in the form of wave nature. Now what does this theory say? That particle is in constant motion inside the nuclei, but would have finite probability of penetration. The probability, although the probability of penetration is very much small, but there is a probability. That is the basic reason behind the Gamow theory of alpha decay. Now as we have already studied that the decay constant, which is directly relation to the collision frequency and the transition probability. Collision frequency we have already studied, which is directly proportional to the velocity and inversely proportional to the radii of the nuclei, and where T is a transmission probability, and which is directly related to e raised to power minus of 2k2 into L. Although this expression comes quantum mechanically, the quantum mechanical expression for this transmission probability is this one, but we will consider this factor as equal to 1 because this factor is playing its major role. So we will neglect this factor and is considering is equal to 1. So transmission probability would be e raised to power minus of 2k into of L, where L is the length of the barrier and k2 is a wave vector inside the potential barrier. Suppose L is the length of the barrier, that length the alpha particle has to cross, and k2 is the wave vector inside the potential barrier, wave vector which is associated with our alpha particle. So K2 is a wave vector which is associated with a wave vector inside the potential barrier, and which can be expressed quantum mechanically as can be expressed as quantum mechanically as under root of 2m into of u minus e upon of h cross. So T can be written as e raised to power minus of 2k into so T can be written as T can be written as e raised to power minus of 2k2 into of L. We will consider the log on both sides. We will get log T is equals to minus 2k2 into L, and we can also integrate this value of L. We can also write it as that is a k2 as a function of r, and its r is varying from 0 to L because the length of the potential barrier is varying from 0 to of L, and we can also consider it is in this form like varying from r naught to r. Now let me explain how this 0 changes to r naught and L changes to r. Now let us study this graph. Suppose this is a potential barrier from 0 to r naught. In this case, suppose this is a wave function which is associated with the alpha particle, and uh, before colliding it with the barrier, the wave function starts moving towards a complete length that is r naught, and the potential